After these fundamental breakthroughs, both of these groups have done a lot of work, and they have constructed more and more complex structures and more functional structures. Just to give you a couple of examples out of very many. Sauvage group have, for example, designed a molecule, constructed a molecule which can extend and contract dramatically in a very controlled manner. And this is actually mimicking the function that we see in our muscle tissue. So we can call it a type of molecular muscle. And the Stoddard group, they have done many things. One example they made was a so-called molecular elevator or lift, where you have a plane in red here that can move between two stations upon external stimulus like so. So, one component in a machine that is very, very important is the motor component, and especially maybe the rotary motor component, and in particular, a component that we can rotate only in one direction. And that is a fundamental challenge, and that challenge was met in 1999 by Ben Feringa and his group. So what they could do in this particular case was that they made a molecule, they built in asymmetries in the molecule, and they had two rotor blades, as you can see here, connected to what is called an isomerizable bond, a bond that can change. And using this structure, they can get unidirectional rotation. And the way this works is that when you shine light to this molecule, the rotor blade will flip over, like so, almost 180 degrees. There you see. And that will create tension in the molecule, as you can see here. The molecule doesn't like the tension, it wants to release the tension, and that happens in the thermal step, which is irreversible, pretty much irreversible. And then you have another pulse of light coming in. You get another flip of the rotor, you create more tension, and then in the final step, you have a thermal relaxation again, and then you're back at where you started. And this cyclic moment you can do over and over again in a very unidirectional rotation manner. After this fundamental breakthrough in 1999, the Feringa group and other groups have been working continuously on this field, and they have perfected their structures even more. So nowadays they have structures that can rotate very fast, up to 12,000 revs per second. They have motors that can rotate in either direction. They can also change the direction at will if they want to. They have also worked with, they also show that you can use these molecular motors, these tiny molecular motors, to rotate much, much larger objects, as you can see here. Here you have a glass rod, and this glass rod is in micrometer size. That means that it's 10,000 times larger than the little molecular motor. And as you can see, the motor action can actually be used to drive the rotation of this very large rod in comparison. And the final example I have for this from this group is a more playful example. And what they wanted to show here is they wanted to demonstrate that you can control the motion of a small machine on a surface. And what they actually did then was that they constructed a molecule where you have an axial type of structure, and in each corner of this axial they connect a motor component. So what this then will look like is some kind of four-wheel drive small molecular car. And the way they imagine this to work is you can see on this cartoon where you can see that this structure can move along the surface in this manner. And this particular machine or molecule is exactly what you see here. That's what you see, the machine moving along the surface. So what this